Okay, so last time you started talking about soft SVM, and so actually we talked about SVM and its dual, and we talked about why it's called a support vector machine. And looking at the dual, you had this dual problem where you would end up looking at a gram matrix in the XIs, basically, the examples. And so we talked about the fact that if you sort of replace this inner product with a general kernel matrix, then you can still solve this dual problem. And this sort of corresponds to assuming that there is a feature map that maps the XIs to some high dimensional space, such that in this new domain you have linear separation. And so we want to move on and talk a little bit about what kind of spaces basically you're getting if we do something like this. So if you look at some kernel function and you solve this SVM, what are these functions that you're sort of looking at, like these type of phi x's that you're looking at? So we try to make this more precise. I'm just going to move on to this topic. So the way to formalize this, via this idea of reproducing kernel Hilbert spaces, or let's say RKHS for short. And in order to do that, I'm gonna sort of have a detour to discuss some ideas from functional analysis, and then go back to the definition of the RKHS. So the first thing that we know or we need is the notion of a Hilbert space. So Hilbert space is like the infinite dimensional analog of the Euclidean space. So infinite dimensional analog of the Euclidean space. So what it means is that it's a vector space. So vector space endowed with an inner product. So these all have axiomatic definitions. So vector space has the vector addition and the scalar multiplication, and these two operations sort of together satisfy the usual properties. And then the inner product has it's a bilinear form, which is positive semi-definite and also like faithful in the sense that the inner product, if it's zero, it implies that X is the zero of the Hilbert space. And so based on the inner product, you can define a norm, which is just basically the square root of the inner product of X itself. And so it's also a normed space. And Hilbert space is an inner product space. So a vector space plus an inner product, which is complete with respect to this norm. So what does it mean to be complete? You guys remember? Yeah, okay. Quotient sequences converge. Basically, if you have a sequence Fn such that basically limit Cauchy means, let's say X. So you have X n in the Hilbert space. If Xn minus Xm, so the limit as m and n go to infinity, basically this is zero. So if you want to make it more precise, given like n epsilon, there exists a sufficiently large integer such that if m and n are bigger than that integer, then this deviation is less than epsilon. So these are Cauchy sequences. The elements of the sequence get close to each other, but it could be that there's no limit. So there's nothing in the space to which they converge. A completed space is a space in which every Cauchy sequence has a limit. So there is a point that they converge to. And if you have a like an inner product space, you can always complete it. There is like an abstract completion. You can always make it into a Hilbert space by sort of defining for every Cauchy sequence. So Cauchy sequences form equivalence classes. So two Cauchy sequences are equivalent if they also approach each other. So you get the equivalence classes of Cauchy sequences, and you just define the limit of the Cauchy sequence as that equivalence class. And this just enlarges the class, like the space. And so there's this abstract Hilbert space. And usually you want to sort of, let's say, describe the Hilbert space that you get out of these completions more concretely. So a lot of the functional analysis sort of goes into trying to characterize what a completion of a inner product space is, and we're going to do some of that to build the RKHSs. But there's, in general, when you like have a vector space, you have an inner product, you can always complete it. You get a Hilbert space by identifying Cauchy sequences with each other and sort of calling the equivalence class the limit, basically. Okay, any questions? So we have a Hilbert space. Then there's this notion of linear functional. So phi is a linear functional if it maps H to R. And the key result here is that these statements are equivalent. So phi is continuous, which basically means that if, let's say, so you know what continuity means. So you can think of it in terms of sequences or just continuity at a point. So it's going to be everywhere continuous if it's continuous at 0. So for example, being continuous at 0 means for every epsilon, there exists a delta such that if x is, the norm is less than delta, then phi of x is less than epsilon. Okay, and then you can define continuity at every point similarly. Sorry, so what this is saying is a linear functional is continuous at 0 if and only if it's continuous everywhere. And so you can see by shifting around, this is easy to show. And it's also continuous at some point. So being continuous at 0, being continuous at some point, being continuous everywhere are the same. And the interesting thing is that they're also the same, like equivalent to phi being bounded, which means that there exists a constant such that the norm of phi h, sorry, the absolute value, this is a real number, is bounded by this constant times norm of h for every h in the Hilbert space. Okay, so this might not be that obvious at first, but you can see from the definition continuity at 0. For example, this holds, then you're definitely going to be continuous at 0. And the rest you can prove, the vice versa. Vice versa is not that obvious. So if it's continuous at 0, then you would get that it's bounded. So being bounded and being continuous are basically the same for a linear functional. And so you're going to use them interchangeably. Okay. We can also define the norm of a linear functional as the supremum of these values as h varies in h, and the norm is being bounded by 1. Another way of saying is that it's the smallest c that satisfies this. And so this norm conveniently is finite if and only if phi is bounded. So that's really easy to see. I can just restrict here to all the phi h whose norm is bounded by 1. Because phi is linear, so scalar multiplication comes out. So a linear functional is bounded if and only if its norm is finite. And then in that case, it's also continuous. So continuity and boundedness are the same. So any questions? All good, online people. Okay, so the next idea is the idea of projection. So if you have a set C, the projection of an element H in the Hilbert space onto the set C is the closest point of C to H. So it's basically the point that minimizes basically this. So if you think of the like, let's say G maps to norm G minus H, the minimizer of this function basically over G. Any minimizer is a projection, and if C, the subset, is closed, non-empty and convex, then the projection is unique. So for every H, there is a unique projection. And in particular, the case of interest for us is if this is a closed linear subspace. So this closed linear subspace is automatically non-empty because it always has 0 in it. So this is a special case. So there is a projection. There is a unique projection onto M. And the interesting thing is that this projection is also characterized by this orthogonality principle. So the closest point, so if I define this operator that maps H to this unique projection of H onto C, so PC of H projects H to C, then this is defined equivalently as saying that H minus H hat has to be orthogonal to M. So this orthogonality principle is equivalent to projection onto a linear closed subspace. So projection onto a closed linear subspace in the Hilbert setting is equivalent to orthogonal projection. So the closeness here is because H could be infinite dimensional. So if M is finite dimensional, then it's automatically closed. But if the linear subspace is infinite, so if the Hilbert space is finite dimensional, everything is like closed. So all the linear functionals are continuous and bounded. All the linear subspaces are closed. So every linear subspace has a projection. When H is infinite dimensional, there could be linear subspaces that are not closed. Then you would have a problem. But if you close, so if you look at the closed linear subspaces, then everything is similar to the finite dimensional case, sort of. So we get this result that if M, I'm not proving these, but just listing some of the properties. So if M is a subset of H and it's closed, linear subspace, for every H, that's P of H. You can think of it as also P. Both notations work. So for operators, usually you don't write the parentheses. So PH be the projection onto M. Then P is a linear operator on H. P is a contraction. It's not a contraction, it's like called non-expansive, basically. So the norm doesn't get large. If it was strictly less than 1, it would be contraction. Less than H would be contraction. But this is saying that the operator is non-expansive. P is idempotent, so P squared is equal to P. So if I project twice, so P squared is like P times P, like PH, and then another P. So P squared H is basically PH. So this is saying this has to be PH, because projecting twice doesn't change the object. And then the kernel of P is going to be M perp. The range of P is going to be M. So M perp is the orthogonal complement of M, so the set of all H, such that H is orthogonal to M. And what it means is that H is orthogonal to every element in M, and orthogonal means, you know what this means, right? So H orthogonal to F just means that inner product is 0. Okay, so so the fact that the kernel of P is M perp and the range is M, and then there is this orthogonal decomposition into the kernel and So basically the range of P would be the kernel of P perp. And so, the end result is that if M is a closed linear subspace of H, then the Hilbert space, then for every H we have this orthogonal decomposition, this unique decomposition where the first component is in M. Basically this is the projection, so H is like projection onto M of H, and the second component is in the orthogonal complement of M. Okay, that's sort of intuitive, but it just generalizes to any Hilbert space if the subspace is closed. And again, if the subspace is linear and closed, then the M perp is going to be M. A better thing to say here is that if, in general, if it's not the case, then I believe M perp would be just the closure of M. That's the more general thing. So the M perp is always closed. So start from some M, the M perp is always going to be a closed linear subspace, no matter what M is, because this relation sort of, you can see this relation is sort of continuous in a sense. So if you have a sequence that's in M perp, then you can take the limit of both sides, the inner product using the Cauchy-Schwarz, the limit goes inside the inner product. So M perp is always, so this is always linear closed for any M. So we start from M perp. So M is not yeah, so let's see. Yeah, how can you argue? I don't want to argue. So let's say this is true. Yeah, what I want to say is that in general, M perp is going to be the closure of M. So the closure is just the M together with all the limits of the sequences in M. You can try to argue this for yourself. The thing is that this has to be closed because M perp always makes things closed. And it has to contain M, but then you can also argue that it shouldn't be larger than M perp, like M bar. So just argue this for yourself. Then from this result, it follows that if I start from a linear subspace H, I can say that this A is dense in the Hilbert space if A perp is 0, like the identity 0. So this is the key result that they're going to use. This result and this is key. So why this is the case? Because, so suppose A perp is 0, right? Then A perp is going to be 0 perp. You can easily see that this has to be the entire H. And this is just A bar. So this is saying that the closure of A is H, that's the meaning of being dense in H. Vice versa, if it's dense, it means that A bar is equal to H, right? Then I probably do this. Perp would be 0 because I take the perp of both sides. H perp would be 0, and then I want to say that the closure of A perp and the perp okay. What can we do here? I want to say that right. So the closure of a perp is the same as a perp. That's because a perp is always closed. So if I take the closure and then perp versus a perp is going to be the same, I believe, then this would be true. So if A is dense, this is equivalent to this, and this implies that if this is the case, then this is true again. In any case, so try to argue this for yourself. It just follows from the fact that perp would be m bar, and then taking the perp always makes things closed, sort of. Okay. So the take-home message is that if I want to show that something is dense, like if it's a linear subspace, if I take the perp and it turns out to be only including a 0, then it's dense in the Hilbert space. Questions? Okay, so this is the recap. Now we get to this interesting result that says that if I have a bounded linear functional, or you can say like equivalently continuous linear functional on a Hilbert space, then there exists a unique H naught in the Hilbert space such that this phi of H is the inner product of H and H naught for every H. And the norm of phi would be the norm of H. So this is the norm of the functional, right? So this is defined as phi supremum such that norm H is less than or equal to 1. So the space of bounded linear functionals on H is called the dual of H, and this norm, functional norm, is just the norm of the dual, basically. The thing is that dual norm is the same as the norm itself, and this is the Hilbert norm. Norm of H. Okay. So what this is saying is that every linear functional can be represented uniquely by an element of the Hilbert space. So, this dual space is the space of like all linear functionals on H, and the Rees representation theorem says that this dual space is basically isomorphic to H itself. So for every linear functional, there is a unique element in the Hilbert space that I can use. I can take the inner product, the elements in H with this, and this generates the linear function. So this is rather sort of trivial in the finite dimensional case, but it's not that trivial in the infinite dimensional case. Does that make sense? Okay, so let me just give you the proof. The proof is like simple. So the first thing to note is that the kernel of phi is, so what is the kernel of phi? How does the kernel define? Or how is it defined? Kernel of phi. Yeah, so all the H's in H such that phi of H is 0. So the first is that this is a linear subspace. The fact that it's linear is simple. It's also closed. Why is it closed? So actually have the so if I take Hn in H, and Hn belongs to the kernel of phi, right? So this means that phi of Hn is 0 for every n, right? To show that if it's closed, suppose these have to be like, okay, so this is in H. Every element is in the kernel, and Hn converges to some H as n goes to infinity. So this is in H. We want to show that this limit is also in the kernel. So we know that this is the case. Then I take the limit of both sides. Phi of Hn. Definitely this is 0. and this is equal to phi of h because phi is continuous, right? So that's where it goes. So then h has to be in the kernel. So if you have a continuous or bounded linear functional, then the kernel is closed. It's a linear closed subspace. So next we assume that this kernel is not the entire H. So if the kernel is the entire H, what does it mean? Then the functional is just zero everywhere identically, and I can take this H naught to be just the zero element. Right? And it's not hard to see that that's the only element that works. So that case is trivial. So assume that the kernel is not the entire H, and then the kernel perp is not going to. So the perp of this is not going to be the perp of H. So the kernel of phi perp is not going to be. This is the perp that. So I'm taking the perp of both sides. So I get this because the perp of H is zero. The set of all vectors that are orthogonal to entire H is just a zero set. So that's the case. So because it's not entirely trivial, there is a non-zero element. So I can find a non-zero element in the kernel of phi. So there is an f naught in the kernel of phi, which is non-zero. And I can, without loss of generality, assume that phi of f naught is equal to 1. So why can I assume that? Yeah, so we can rescale because phi is a linear functional. We can always rescale if not to make phi of it to be anything you want. So we make it equal to 1. Okay, now the idea is that this is sort of almost there. So this phi naught after proper normalization is going to be h naught. So pick any h in h and let alpha be the phi of h. Then we look at the phi of h minus alpha if not. So this is 0. Why is it 0? By linearity, so this would be phi of h minus alpha phi of f naught. And if you define the way that we define this, so this is 1, and this is alpha, so this whole thing is going to be 0. So this means that this guy is in the kernel of phi, right, as well. Not as well, but it's in the kernel of phi. So then I have this. Why is that true? Yeah, because f naught is in the kernel perp, and this is in the kernel of phi, so that's the definition of perp. So f naught is orthogonal to this guy, and then I just expand this by linearity of the inner product, so you get this minus that, right? And so what is the next step? I just rearrange this, right? So we get that, so rearrange this inequality that we get phi of h is equal to h f naught minus f naught squared. I can divide by norm of f naught because f naught is non-zero, right? And so I get that this is f naught divided by f naught squared. And so this is, I can define it to be h naught. So this f naught does not depend on h. So I just depict the one that exists in the kernel phi perp. Right. So we showed that this exists. And the uniqueness you can argue as an exercise. Suppose there are two, it's easy to show that this has to be unique. We showed the existence. So every linear operator that's bounded can be represented like this. This is called Ries's representation theorem, and just equivalently, so theorem 3 implies that like HS star is isometrically isomorphic to H. Basically, the dual of a Hilbert space can be identified as a Hilbert space. So it's a space of linear functionals on bounded linear functionals on Hilbert space is like, again, you can think of it as a Hilbert space, which is identified with the original space. So every element in the Hilbert space, you can think of it as both in the Hilbert space and also the dual in the dual. So it defines a linear functional. That's basically how we view the usual Euclidean space, right? So every element you can think of it as the normal of a hyperplane or linear function. Questions? Okay, so this is the detour. So now we're going to use these to study the notion of an RKHS. So an RKHS, so let X be a set, just a general set. And I'm going to use this notation for simplicity to denote all the functions, real valued functions on X. You can think of this as infinite dimensional vectors indexed by X. That's why I use that notation. But it's just a set of all functions on X. So the Hilbert spaces that we're going to look at are subsets of this space of functions on X. So we're going to look at functional spaces, and we care about functional spaces that are Hilbert space in a sense. So Hilbert, a subset H of this, so the space of functions on X is called a reproducing kernel Hilbert space, or RKHS for short, if H is a Hilbert space first. So it has an inner product. So it's a vector space, has an inner product, it's complete with respect to the inner product, all that. And then moreover, that's the Hilbert part. So far it's a Hilbert space. The reproducing kernel part is the second property, that for every X in little x and X, the evaluation functional, which is defined here, is continuous. So the evaluation functional, for every X, it's a linear functional. It's a particular linear functional, which is defined as taking every f, outputting the value of f at X. So it operates on the functions, it evaluates them at point X. So you fix X, this defines a functional. You change X, it's a different functional, right? So all these functionals for different X's, so you have a collection of them. Basically, for every X in script X, you have one of these functionals. All of these are continuous, or you can say bounded. Okay, that's an RKHS. Okay, there is an immediate consequence that then they can be represented by an element in the Hilbert space via the Ries's representation. We'll get to that, but that's the basic. That's one way to define the RKHS. So they're Hilbert spaces of functions in which evaluation functionals are bounded. Okay, so far makes sense. I want to give some examples of this and then talk about the Ries's, the consequence of the Ries's representation here. So if you have an RKHS because the evaluation functionals are continuous, this means that the convergence in the Hilbert norm, so this has an inner product, right? Inner product. Hence there's a norm. Sometimes I just write this, or I can write something like this to emphasize. So what this is saying is the second property, so B, B basically implies that convergence in the Hilbert norm is stronger than pointwise convergence. So if a sequence of functions converges in the Hilbert norm, then it converges pointwise. So why is this the case? So suppose there exists a sequence of functions Fn, subset the Hilbert space, and I know that Fn converges to some f let's say in the Hilbert space. F is also in the Hilbert space. Okay, I want to conclude that Fn of x converges to F as real numbers for all x. So how can we argue this? Okay, so let's look at the difference. Okay, what next? We can do what? Yeah, so these are evaluation functional is a linear functional. You can see it. Let's not do that yet. Right, we'll do that later. But this is the evaluation functional, right? So what this is saying is that if the delta x is continuous, right? What it means that if Fn converges to F in the Hilbert space, then basically delta x Fn converges to delta x F as real numbers. I mean, you can say if this side is another way of saying it is like Ffn minus F. I can make it less than delta such that delta Fn minus F is less than epsilon, right? But we don't need to, yeah, just this is enough. This is continuity, right? Later on, we can use this to get better estimates. But this follows from the fact that delta x is a continuous linear functional. Right, so convergence in H implies pointwise convergence. So if I have a sequence of functions, so you have a Hilbert space, you have a sequence of functions that converges in the Hilbert norm, but does not converge pointwise, then it can't be an RKHS. Okay, so here's a non-example. So suppose we have pre-L2 space on 0, 1. So all the continuous functions on 0, 1 equate with the L2 norm. So that's the L2 norm. So all the continuous functions for which they're in 0 to 1, they're integrable, bounded, hence integrable. Or it's just easy to see the continuous function. This integral makes sense. So the L2 norm, we can define it on that space. And we can also argue that this space is not complete. The completion would be identified with the L2. So that's like the measure theory achievement there. But let's say, can we make it into an RKHS, or is the completion an RKHS? Is the L2 basically an RKHS? So there's the completion is sort of unique in a sense. So you can complete it with respect to this inner product, and then you can ask whether the resulting functional space is. So it's roughly saying. So completion is L2 of 0, 1 because this is dense in L2. Or that's how like you. So what it is saying is that can we do L2? So one issue is that L2 spaces of L2 is the spaces of equivalence classes of functions. They're not functions really, because once you go to the completion, the functions are not pointwise defined. You can also see, like, from a definition of the integral, that if you manipulate on a set of measure 0, then things would not change. But if you think about how in analysis this is constructed, that the elements are not functions, they're equivalence classes of functions modulo almost sure convergence. Sorry, almost sure equivalence, sort of. That's one view of L2. So we have that issue, but let's ignore that issue for now. And see this example that this cannot be an RKHS, because I can come up with a sequence of functions in this space. So this is the sequence that we have. I've plotted it here. This is a sequence of continuous functions on 0 to 1. For every x, basically fixed x. Here x is this is x. I think this should be 0 to 1. This is like 1/4. Okay, so I'm plotting these for x equal 1/4 here, but then you can change x. So as n goes to infinity, these are continuous, but just they narrow down. So you can see that fn of x is 1. So this sequence at point x is always 1 for all n, but the L2 of the sequence shrinks to 0. It's not hard to see that it's basically the mass goes to 0. And this shows that the space cannot be, or the completion cannot be in RKHS. Because the completion will have, the norm would be the same as, so when you complete the space, the norm is extended, doesn't change on the original space. So you'd have a Hilbert space whose norm would be L2 for these. It goes to 0 on the sequence, but the evaluation at x doesn't converge. So fn of x has to converge to the limit at 0, which is 0, but doesn't go. So the completion of this space cannot be in RKHS. Okay, so the L2 space of on 0, 1, for example, is not in RKHS. This is without defining, without like looking at kernels and stuff like that. It's just you have a linear space of vector space of functions. It's a Hilbert space. You can ask whether it's an RKHS by looking at the evaluation function. Any questions? Okay, so what is an RKHS? So here's an example where it is an RKHS. So consider the functions on 0 to 1. Real value at f0 is 0. F is absolutely continuous, which I refer to analysis. What is the definition? This is basically, it's like stronger notion of continuity. So if you partition the space 0, 1 into a partition, then the sum of the deviations of the functions at the endpoints of the partition is controlled if the sum of the lengths of the partitions are controlled. So let's just look at this is basically the definition for which the fundamental theorem of calculus works, the set of all functions for which the fundamental theorem of calculus works. So if f is 0 at 0 is absolutely continuous and the derivative. So if f is absolutely continuous, then the derivative exists almost everywhere. And moreover, so f absolutely continuous implies that f prime exists almost everywhere, and moreover, f can be written as the integral of f prime plus a constant. So the fundamental theorem of calculus works for, so these are the classes of functions basically. This is more or less like an equivalence. A function is absolutely continuous if only if prime exists almost everywhere, and the integral of it is the function. So these are the functions that can be written as the integrals of their derivatives. So moreover, we assume that f prime, which all exists almost everywhere, is in L2. Then this defines a class of functions. On this class, I can define an inner product by taking the basically integral of, this is like the L2 norm between the derivatives of the two functions. Because f prime and g prime, so suppose f and g are in H, then f prime and g prime are by definition in L2, so I can define the inner product on H as the L2 inner product between the derivatives. Okay, that's well defined. Next, we note, because of this fact that I mentioned, the fundamental theorem of calculus basically here, that if f is in H, then basically I can write, so f of x would be integral from 0 to 1, f prime of t dt. So this would be like f of x minus f of 0, but f of 0 is 0, right? So we have this by that boundary condition. And so I can rewrite this as integral, sorry, this is up to x. That's how I usually write it, but this I can write as 0 to 1. F prime of t indicator t is less than x dt. Okay, that's what I can do. Right. Then what we can do is we can call this. This is the same thing that I wrote there. So if you look at this, if I treat this as the derivative of another function, the function depends on x, but it's a function of t. If I think of it as the derivative of something, then this is really f and k prime. Okay, and this is suggestive. This is like, sorry, f prime and k prime, L2, right? So this is, if I can do that, then yeah, so let's not do that. Okay, we'll do that later. So this is some other function, right? So it's some sort of gt, fixed x for now, right? Or sorry, yeah. So this is like, so I can use the Cauchy-Schwarz here, right, for the L2 space. So this is so I want to use Cauchy-Schwarz to argue this. How can I do that? So we have f of x is 0 to 1 f prime of t indicator t starting with x dt. By Cauchy-Schwarz in L2, this is like integral 0 to 1 f prime t squared dt square root times integral 0 to 1 indicator squared, which doesn't change, dt square root. Right, so this is the, by definition of this inner product, this is the Hilbert norm. So this is like the Hilbert norm squared, and not squared, just this. And this guy is just root integral from 0 to x dt, which is just root x. Okay, so we get something like that. So this holds for every x. So this shows that the evaluation functional is bounded, and this is nothing but delta xf. Right, so this is showing that the evaluation functional is bounded and the norm is at most root x. So whatever constant there is, that's the norm. Moreover, it shows that the inner product is actually a valid inner product, because if the inner product of f and f is 0, from this we see that the norm of f is 0, and so f of x has to be 0 identically for all x. And so this shows that the inner product is faithful. So it's like really an actual inner product. So so we have an inner product, a space in which the evaluation functionals are bounded. The only thing that you need to show that this is an RKHS is to show that this is actually a Hilbert space with respect to the inner product. So you have to show that it's complete. Just want to show that. So far it's clear. So the fact that this is inner product is easy because it follows from the derivative is linear, sort of, and L2 is an inner product. So this is an inner product. The only thing that you have to verify is this faithfulness, which follows from what I did there. And then the evaluation functional is also continuous or bounded on this space. We just have to show that this is complete to make sure that it's in Hilbert space. This is also easy to show. So pick a Cauchy sequence in H. So we now want to verify that Cauchy sequences converge. By the inequality that we just had, so we have basically fn x is less than or equal to root x fn in the Hilbert space, right? Because we're Cauchy in this norm, so this is just saying by that inequality you would have like fnx minus fmx is less than or equal to root x fn minus fm, right? So if we're Cauchy in the Hilbert space, which means that this norm is going to 0 as m and n get go to infinity. And this side also does that. So the pointwise sequence is Cauchy, right? Because it's Cauchy, it's pointwise Cauchy, I can define the limit, pointwise limit. So pointwise limits exist, and that defines a function. That's the first step. Then next we argue that f prime is Cauchy in L2. That's the definition basically. F is Cauchy in H, f prime is Cauchy in L2, because the norm of the H is the L2 norm on the derivatives. And so f prime n has to converge to some g in L2 because L2 is complete. Right, so this is complete. We know that L2 is a Hilbert space, so this is complete. So f prime converges to some g in L2. So convergence is also in L2. So conversion in L2 to some g in L2. Next we have, this is by the definition of f, pointwise limit. So why this equality holds? So fn is in H, and so we have this representation, right, for every f in V. Right, so I just do the integral representation. Just should replace this with that. So the idea is that the limit of this is equal to that. So why is that? This is just basically inner product of fn and some function, call it like h in L2, right? H is just indicator t less than or equal to x, right? So this is saying this converges to gh in L2. So what this is saying is, because fn prime converges to g in L2, this is just saying this holds if this is if this thing is bounded like continuous linear functional in L2. But this is always the case. So things that look like this, by reuse the representation theorem, anything that looks like this is a continuous linear functional. So continuous linear functionals are in one-to-one correspondence with things like that. So this is a continuous linear function. It's also like easy to show that this is continuous from Cauchy-Schwarz, right? So this is continuous in L2. Fn prime converges to g in L2. So this is true. So this limit converging to this is just the fact that taking inner product with a function is a continuous linear function in L2, and the sequence converges in L2. So, and then if you look at this, fn, we have shown that fx is equal to this. And so by definition, f has to be absolutely continuous. Anything that can be written as an integral is absolutely continuous. The derivative by fundamental theorem calculus is equal to g almost everywhere. And we also know that the derivative, which is g almost everywhere, g is in L2, so the derivative is in L2. So we show that f is absolutely continuous. The derivative is in L2, and f0 is also the limit of fn0. Because of this, if you evaluate 0, it's just these are in this space, so these are 0. So the boundary condition also holds. So this means that conclude that f belongs to H. So we started with a Cauchy sequence, constructed a limit that's in H. And so the space is complete. Okay. So this space is an RKHS. The only thing that we did is to show that there is an inner product for which this is a Hilbert space, and the evaluation functional is bounded. So now we have an example. Now let's go to the definition of the RKHS, combining this definition. This definition with the reused representation theorem. So if you have an RKHS, by reused representation theorem, because the evaluation functional is continuous, I can write the evaluation functional as f inner product with some element in the Hilbert space. So for every x, there is an element kx in the Hilbert space such that the inner product of f with this kx is f of x for every f. So this is the representer of evaluation basically at x. And so this is the key point in RKHSs. So in order to evaluate the function, you can just take inner product with some function in the Hilbert space. This makes like evaluation like the linear algebra basically. It is very powerful. That's the key idea. Once you get comfortable with it, just you treat the functions as vectors. If you want to evaluate them, just take the inner product with some other vector. You evaluate at that point. Now, if I look at this, so kx is basically a function itself, right? So kx is a function because it's an element of is a function on x. So I can write it as like kx of y. So there's an argument. So for every y in h, I can evaluate it. So this is like this for every y in h. So if I look at this, I have two arguments, one x here, one y here. I can define a bivariate function on x, which is like kx of y. This is called the reproducing kernel of h. So you have an RKHS. You represent like a linear evaluation functionals by your representer. This representer for every x is a function. So you have two arguments. You look at this. This defines a kernel. We'll see. It doesn't matter which way you define it. This turns out to be symmetric. But then by this definition, so every RKHS has a reproducing kernel. Why this is called the reproducing kernel? Because we have this reproducing property. If you just plug in, so I can now write this as, by definition, it's just k dot x. So if I look at this kernel, sorry, or the other way around. Later on, it doesn't matter. So if I fix x, put a dot here, which means that I'm viewing this as a function of, so this is a function y maps to kxy. That's the meaning. So if I have this kernel, if I look at it as a function of y for fixed x, that's the representative evaluation. So I get this here, right? So this I can write using this notation as this. So this is called the reproducing property. So if you have this bivariate function in the kernel, such that when you fix the one element at x, this is this is a function in h by definition. So this belongs to h for all x in x by definition. So this is a function in h. Take the inner product with f. It just evaluates f. So this is called the reproducing property, and this is why it's like these things are called reproducing kernel Hilbert spaces, because there is a reproducing kernel. There's a kernel with the reproducing property, which means this. Okay, so far so good. Okay, one more point is if I apply this to this reproducing property to the function f, which is, let's say, ky, right? So if I do k y dot and then kx dot, so what will happen? Because ky dot is also an element in Hilbert space. I'm going to evaluate this at point x, right? So I get k y x, right? And also, like, this is also going to be equal to, like, inner product is symmetric y dot. So this is also k xy, right? You see that the kernel function is symmetric. And the way you're writing is just, this is ky, this is kx, right? Kx y. So first it shows that it's symmetric. Next it shows that it's also positive semi-definite, because I can write the kernel function as this, as an inner product of these things. It's a positive semi-definite function. What it means to be positive semi-definite, it means that if I pick a sequence x1 up to xn in x, and if I form this kernel matrix, which is the kernel evaluated at xi, xj, this kernel is a positive semi-definite matrix. Okay, so this property that you can write the k as this. This shows that it's a positive semi-definite matrix. Why is that? I have to show that kxi, xj, this matrix is positive semi-definite for every sequence xy. So this is one to show that this is PSD. So how do I show that this is PSD? We need to show that something like ai, aj, kxi, xj is non-negative for every sequence ai, right? Next, this is like inner product k, xi, k, xj, inner product in the Hilbert space. So is this positive semi-definite? Or is this like, how do I proceed? Yeah, by linearity, you bring in everything, you just can confirm that this is in fact just this, right? What is this? Norm squared of this guy, and this is definitely positive semi-definite. So these are in the Hilbert space. Right? So the fact that I can write it as the kernel as inner product of these kernel representers immediately means that any kernel matrix that I construct is positive semi-definite, and that's the definition of a positive semi-definite function. We also see it's symmetric because the inner product is symmetric. So this leads to this definition. A symmetric function k is called a kernel if it's a positive semi-definite function. You can remove the symmetry if you're looking at complex numbers. It would be like anti-symmetric, basically. It's like sesquilinear sort of. But for real valued cases, the inner product is real valued. So you look at symmetric functions, they're kernels if they're positive semi-definite. So this argument says that the reproducing kernel of an RKHS is really kernel in this sense. Okay, so it's a positive semi-definite, symmetric positive semi-definite function. The inverse or the converse is also true. So if you have a symmetric positive semi-definite function, then there is an RKHS for which that function is a reproducing kernel, and this relation is actually 1-to-1. So in the end, what happens is that for every kernel function, which is a symmetric PSD function, there is a unique RKHS for which that kernel is a reproducing kernel. Next time, I'm going to try to prove that. That's this result, which is like one of the fundamental results in this classical theory of RKHS, that if you have a function which is a kernel, bivariate function is a kernel, there exists an RKHS on X whose reproducing kernel is K. The reverse is that if you have two kernels, if you have two RKHSs with two different kernels, if the two kernels are the same, then the Hilbert spaces are the same, which means that if you have two different RKHSs, then the kernels have to be different. So this shows that there is a 1-to-1 correspondence between kernels and functions. So for every kernel function, there is an RKHS, and that RKHS is uniquely associated with that kernel. If you change the kernel, so next time I'm going to come back and talk a little bit about the proof of this. And he also drives the kernel of the sublet of 1. And so that would just conclude the basic properties of the RKHS. Okay, sounds good. Questions? Okay, thank you. See you next time.